In mathematics, a bivector or two-vector is a quantity in exterior algebra or geometric algebra that extends the idea of scalars and vectors. If a scalar is considered an order 0 quantity, and a vector is an order 1 quantity, then a bivector can be thought of as being of order 2. Bivectors have applications in many areas of mathematics and physics. They are related to complex numbers in 2 dimensions and to both pseudovectors and quaternions in 3 dimensions. They can be used to generate rotations in any dimension, and are a useful tool for classifying such rotations. They also are used in physics, tying together a number of otherwise unrelated quantities. Bivectors are generated by the exterior product on vectors. Given two vectors A and B, their exterior product AB is a bivector, as is the sum of any bivectors. Not all bivectors can be generated as a single exterior product. More precisely, a bivector that can be expressed as an exterior product is called simple. In up to 3 dimensions all bivectors are simple, but in higher dimensions this is not the case. The exterior product is antisymmetric, so BA is the negation of the bivector OB, producing the opposite orientation, and A is the zero bivector. Geometrically, a simple bivector can be interpreted as an oriented plane segment, much as vectors can be thought of as directed line segments. The bivector AB has a magnitude equal to the area of the parallelogram with edges A and B, has the attitude of the plane spanned by A and B, and has orientation being the sense of the rotation that would align A with B. History. The bivector was first defined in 1844 by German mathematician Hermann Grassmann in exterior algebra as the result of the exterior product of two vectors. Around the same time in 1843 in Ireland, William Rowan Hamilton discovered quaternions. It was not until English mathematician William Kingdon Clifford in 1888 added the geometric product to Grassmann's algebra, incorporating the ideas of both Hamilton and Grassmann, and founded Clifford algebra, that the bivector as it is known today was fully understood. Around this time Josiah Willard Gibbs and Oliver Heaviside developed vector calculus, which included separate cross-product and dot products that were derived from quaternion multiplication. The success of vector calculus, and of the book Vector Analysis by Gibbs and Wilson, had the effect that the insights of Hamilton and Clifford were overlooked for a long time. Since much of 20th century mathematics and physics was formulated in vector terms, Gibbs used vectors to fill the role of bivectors in 3 dimensions, and used bivector to describe an unrelated quantity, a use that has sometimes been copied. Today the bivector is largely studied as a topic in geometric algebra, a Clifford algebra over real or complex vector spaces with a non-degenerate quadratic form. Its resurgence was led by David Hestenes who, along with others, applied geometric algebra to a range of new applications in physics. Derivation. For this article the bivector will be considered only in real geometric algebras. This in practice is not much of a restriction, as all useful applications are drawn from such algebras. Also, unless otherwise stated, all examples have a Euclidean metric and so a positive definite quadratic form. Geometric algebra and the geometric product. The bivector arises from the definition of the geometric product over a vector space. For vectors A, B and C, the geometric product on vectors is defined as follows. Associativity, left and right distributivity, contraction, where Q is the quadratic form, A is the magnitude of A and A is the signature of the vector. For a space with Euclidean metric A is 1 so can be omitted, and the contraction condition becomes the interior product from associativity A equals A to B, A scalar times B. When B is not parallel to and hence not a scalar multiple of A, AB cannot be A scalar. but as a sum of scalars, and so a scalar. From the law of cosines on the triangle formed by the vectors, its value is a, b, cos theta, where theta is the angle between the vectors. It is therefore identical to the interior product between two vectors, and is written the same way. It is symmetric, scalar valued, and can be used to determine the angle between two vectors. In particular, if A and B are orthogonal, the product is zero. The exterior products, just as the interior product, can be formulated as the symmetric part of the geometric product, another quantity. The exterior product can be formulated as its antisymmetric part. It is antisymmetric in A and B, and by addition, that is, the geometric product is the sum of the symmetric interior product and antisymmetric exterior product. To examine the nature of a B, consider the formula which, using the Pythagorean trigonometric identity, gives the value of 2 with a negative square. It cannot be a scalar or vector quantity. So it is a new sort of object, a bivector. It has magnitude a, b, sin theta, where theta is the angle between the vectors, and so is 0 for parallel vectors. To distinguish them from vectors, bivectors are written here with bold capitals, for example. Although other conventions are used, in particular as vectors and bivectors are both elements of the geometric algebra. Properties. The space lambda-2n, the algebra generated by the geometric product, is the geometric algebra over the vector space. For a Euclidean vector space, it is written or Cn, where n is the dimension of the vector space n. Cn is both a vector space and an algebra, generated by all the products between vectors in n, so it contains all vectors and bivectors. More precisely, as a vector space, it contains the vectors and bivectors as linear subspaces, though not subalgebras. The space of all bivectors is written lambda-2n. The even subalgebra, the subalgebra generated by the bivectors, is the even subalgebra of the geometric algebra, written C plus n. This algebra results from considering all products of scalars and bivectors generated by the geometric product. It has dimension 2n-1, and contains lambda-2n as a linear subspace with dimension 1/2 n. In 2 and 3 dimensions, the even subalgebra contains only scalars and bivectors, and each is of particular interest. In 2 dimensions, the even subalgebra is isomorphic to the complex numbers, while in 3 it is isomorphic to the quaternions. More generally, the even subalgebra can be used to generate rotations in any dimension, and can be generated by bivectors in the algebra. Magnitude. As noted in the previous section, the magnitude of a simple bivector, that is one that is the exterior product of two vectors A and B, is a, b, sin theta, where theta is the angle between the vectors. It is written b, where b is the bivector. For general bivectors, the magnitude can be calculated by taking the norm of the bivector considered as a vector in the space lambda-2n. If the magnitude is 0, then all the bivector's components are 0, and the bivector is the 0 bivector, which as an element of the geometric algebra equals the scalar 0. Unit bivectors. A unit bivector is one with unit magnitude. It can be derived from any non-zero bivector by dividing the bivector by its magnitude. That is of particular interest are the unit bivectors formed from the products of the standard basis. If A and EJ are distinct basis vectors, then the product AEJ is a bivector. As the vectors are orthogonal, this is just EIEJ, written EIJ, with unit magnitude as the vectors are unit vectors. The set of all such bivectors form a basis for lambda-2n. For instance, in 4 dimensions, the basis for lambda-2 is or. Simple bivectors. The exterior product of two vectors is a bivector, but not all bivectors are exterior products of two vectors. For example, in 4 dimensions, the bivector cannot be written as the exterior product of two vectors. A bivector that can be written as the exterior product of two vectors is simple. In 2 and 3 dimensions, all bivectors are simple, but not in 4 or more dimensions. In 4 dimensions, every bivector is the sum of at most 2 exterior products. A bivector has a real square if and only if it is simple, and only simple bivectors can be represented geometrically by an oriented plane area. Product of two bivectors. The geometric product of two bivectors, A and B, is the quantity A. B is the scalar-valued interior product, while AB is the grade 4 exterior product that arises in 4 or more dimensions. The quantity A times B is the bivector-valued commutator product, given by the space of bivectors lambda-2n or Lie algebra over, with the commutator product as the Lie bracket. The full geometric product of bivectors generates the even subalgebra. Of particular interest is the product of a bivector with itself. As the commutator product is antisymmetric, the product simplifies to if the bivector is simple, the last term is 0 and the product is the scalar valued AA, which can be used as a check for simplicity. In particular, the exterior product of bivectors only exists in 4 or more dimensions, so all bivectors in 2 and 3 dimensions are simple. 2 dimensions. When working with coordinates in geometric algebra, it is usual to write the basis vectors as a convention that will be used here. A vector in real two-dimensional space 2 can be written A equals A1 E1 plus A2 E2, where A1 and A2 are real numbers. E1 and E2 are orthonormal basis vectors. The geometric product of two such vectors is this can be split into the symmetric, scalar-valued, interior product and an antisymmetric, bivector-valued exterior product. All bivectors in 2 dimensions are of this form, that is, multiples of the bivector E1 E2, written E12 to emphasize it is a bivector rather than a vector. The magnitude of E12 is 1, so it is called the unit bivector. The term unit bivector can be used in other dimensions, but it is only uniquely defined in 2 dimensions, and all bivectors are multiples of E12. As the highest grade element of the algebra, E12 is also the pseudo-scalar which is given a symbol I. Complex numbers with the properties of negative square and unit magnitude. The unit bivector can be identified with the imaginary unit from complex numbers. The bivectors and scalars together form the even subalgebra of the geometric algebra, which is isomorphic to the complex numbers. The even subalgebra has basis, the whole algebra has basis. The complex numbers are usually identified with the coordinate axes and two-dimensional vectors, which would mean associating them with the vector elements of the geometric algebra. There is no contradiction in this, as to get from a general vector to a complex number an axis needs to be identified as the real axis, E1 say. This multiplies by all vectors to generate the elements of even subalgebra. All the properties of complex numbers can be derived from bivectors, but 2 are of particular interest. First, as with complex numbers, products are bivectors and so the even subalgebra are commutative. This is only true in 2 dimensions. So properties of the bivector in 2 dimensions that depend on commutativity do not usually generalize to higher dimensions. Second, a general bivector can be written where theta is a real number. Putting this into the Taylor series for the exponential map and using the property E122 equals -1 results in a bivector version of Euler's formula, which when multiplied by any vector rotates it through an angle theta about the origin. The product of a vector with a bivector in 2 dimensions is anticommutative, so the following products all generate the same rotation of these. The last product is the one that generalizes into higher dimensions.